Koshelov and Vladik Kreinovich, who are originally from Leningrad like me, and now they live and work like me in the most important place in the world, in the great state of Texas. They work in the area of several areas of computer science and computational mathematics. Actually, yesterday I looked at Vladik's CV and tried just to count his publications, and I reached 200 and there was no end in sight, so I gave up. So the topic of their talk today is Orevkov, Khalfin, and quantum field theory, how constructive mathematics can help physics.
Thank you very much for the introduction, and thanks for the great opportunity to talk. Actually, to us, this kind of has an additional meaning because last year when the pandemic started, that was the next conference that we were planning to go to. We reserved the hotel places, and I was looking forward to eating Russian food that I like very much. And this was the first thing that had to be canceled. So, and I'm glad that even in, at least in the online way, the conference is going on. So this talk will be different and similar for the previous talks. Different because I think most of the previous talks were related to Professor Orevkov's work in logic. This will be about his work in constructive mathematics. What will be similar is that, and I apologize for that, there will be no proofs, but at least I will have some excuse why there are no proofs, and I'll explain that later. And if I forget, please ask me a question. So, how it all started. 1972, Professor Orevkov presented a talk on constructive complex analysis at the seminar at Lomé. And the main results were published in 1974. These were the old days when 2 years could pass between presenting the result and publishing it. Now it's kind of unusual, but in those days it was absolutely normal. So, and what he did is he presented explicit constructive proofs of several main results of complex analysis. First of all, that the theorem that is well known in classical complex analysis, that a function is differentiable if and only if it can be expanded in Taylor series at each point. This is a very unusual feature of complex analysis because, of course, in real line, you can have a differential function which is absolutely not analytical. Two, that again, this is very specific for, not that specific because it's true for real analytical functions as well, that if two functions are coinciding on a non-finite compact set, then they are equal. So we can extend each function from any local area. And three, which was probably the most constructively interesting, that if you have an analytical function on a bounded domain, that you can constructively find all its roots. These results previously were proved by Professor Lifshitz in a more implicit way, but what Professor Orevkov did is he provided a more explicit and more kind of clear, more constructive, so to say, derivations of these proofs, which were very interesting. And again, there, as usual, many kind of originally when constructive mathematics started, which is constructive mathematics, which studying what can be algorithmically computed and what can be not. And many results from, at first, of course, there were negative theorems, but then it turned out that, and Professor Lifshitz's papers showed that, among others, that many results from classical non-constructive mathematics are actually constructively true, that you can actually extract algorithms under some conditions and with some notions from the proofs. And if you cannot extend that, then you can have other proofs which are more constructive. Of course, not everything is constructively true. Some turned out to be false. So sometimes there is a classical existence theorem, but there is no general algorithm for doing that. And it's always nice to know that there are some results when this constructive case happens. So why was this interesting? So this talk, and I'm not even sure that Leonid Khalfin, who was a colleague from Lamy interested in physics, he was kind of specializing in application to physics. I'm not even sure he attended his talk, but I think he saw an advertisement. He saw the abstract, which was posted. Maybe he talked, and he talked to me. Why to me? Because I was always interested in applications to physics. I actually gave some talk at the time about possible relation between constructive mathematics and physics. It was not, these talks were not very well kind of accepted neither by constructive mathematics community nor with physics community. Physicists, they like something more constructive, but looks like Professor Khalfin, he realized that while what I was doing may not be very close to working physics, at least it probably can help. So he asked me the following question, that maybe constructive mathematics can help solve the problem that is related to the use of complex numbers in physics. Now, why this is a problem and why complex numbers in physics? Well, the main, of course, complex numbers are used in many physical areas and applications, but there is one area where they are inevitable, which is quantum physics. In quantum mechanics, it is kind of known that you cannot formulate a theory consistently without going into complex domain. And then what happens is, on the macro level, there are many phenomena in physics which are not smooth at all and not even continuous. I mean, the catastrophic cases like earthquakes and everything, and then everyday things. For example, when I was standing up a few minutes ago and went to make some tea for myself, that's a phase transition. When water goes into, it becomes evaporating, that's a phase transition. It's actually a very discontinuous, very non-smooth phenomenon. Now, on the macro level, on the level of what I see in the kettle, yes, it is discontinuous. Of course, on the micro level, everything is smooth. It is described by the equations in which the right-hand side is smooth and even analytical. So for every molecule of water, there is no discontinuity, it just smoothly goes into different things. But the idea is, while for individual molecules, it's always smooth, from the macro level, some of these phenomena are very fast. And so from the macro level, we perceive them as discontinuous. Why I'm saying all this? Because if you deal with complex numbers, smoothness means analyticity, means the function is analytical. And in quantum field theory, among other things, that has been very successfully used. Why is that? Because very often what happens in physics is, to compute something, you need to compute an integral. The main idea behind that comes from Feynman, who showed that all equations of quantum physics can be formulated in terms of what now is called Feynman integrals over trajectories. And that's a usual kind of most general description of the corresponding physical theories. You might write some equations and everything, but Feynman integrals is what it boils down to. So to compute something, you need to compute an integral. And how do you compute an integral? If you have an analytical function and the corresponding function is usually analytical, it's smoothened. So what you can do is take care of the fact that if you have a function with no singularities inside, then the contour integral over a closed loop is equal to 0. If there are some poles or inside, then you actually have an explicit expressions in terms of these particular poles. And so how can you use that to compute an integral? Well, the problem is, if you try to compute an integral for example, on the real line, the values are complicated, that may be difficult. So what you do is you use a loop. So in the loop, you have some part of the real interval, and then you have a loop that goes to complex infinity. And in complex infinity, Feynman integrals usually become more computable. So instead of computing this difficult compute integral over real numbers, you do an easier to compute integral over the complex values. This idea was pioneered by Nikolai Bogolyubov, professor from Moscow, physicist and more the physicists than mathematicians, and it indeed led to many successful applications. So this is kind of macro, big level use of analyticity. And it actually makes some physical sense. It has been confirmed by many experiments. There was a whole idea in physics of so-called S theory, S for scattering, where basically you kind of try to formulate equations not in local terms, but in terms of these integrals. The problem is that in mathematics, macroanalyticity is equivalent to micro ones. So the fact that every integral over the closed loop is 0 is equivalent in complex area to the requirement that the corresponding dependencies are expandable in Taylor series. Now, the fact that the integral over the closed loop is 0 makes physical sense. It can be confirmed. But this microanalyticity, while mathematically true, from the viewpoint of physics, as Professor Khalfin explained, doesn't make direct physical sense because it kind of refers to local values of the quantities, which, according to quantum physics, according to uncertainty principles, are not measurable. So you have two statements, macroanalyticity, microanalyticity. They are mathematically equivalent. Macroanalyticity has physical sense, microanalyticity doesn't. So what Khalfin suggested is maybe we can have some model in which we do have physically meaningful macroanalyticity, but we don't have physically meaningless microanalyticity. Because of course, what physicists want, they want everything to have physical meaning. They don't want just some mathematical transformation of symbols, which doesn't make any physical sense. And he compared it with, I don't know if other cultures have that. In Russia, we have this fairy tale about Rosa без шипов, a rose without thorns. I've never read it, but it's kind of a common cultural phenomena. Everybody heard about it. And he thought that this may be possible if instead of classical mathematics, we consider constructive mathematics, because in constructive mathematics, some results are indeed not possible. And so maybe there would be no relation between macro and micro analyticity. So unfortunately, in those days, this idea did not materialize. I was not smart enough to immediately understand that, but then he talked to Professor Lifshitz, and Professor Lifshitz pointed out to Khalfin that already was, as was shown in the book by Bishop, one of the kind of founding books which promoted constructive mathematics to mathematicians by Eric Bishop in 1967, that actually constructively macroanalyticity implies microanalyticity and so on. So unfortunately for his dream, this equivalence is true in constructive mathematics as well. So by just simply going from traditional to constructive mathematics, there is no way that you can actually solve this physical problem. And so this idea was abandoned. And just as a phenomenon of culture, that was a kind of funny episode. I may misremember it a little bit, but I remember very well that we were in the same office of Professor Khalfin, me, Vladimir Lifshitz, and Leonid Khalfin himself discussing this. And then Grisha Means walked in, and he made a comment that made us all laugh at that moment. He said, "Что здесь происходит?" Means what is happening on here? Because the idea is you have in the room 3 Jewish guys kind of talking about something, maybe having some Zionist conspiracy at that time. It kind of made us laugh. So anyway, how do you compute these coefficients? Well, again, you can, to compute these coefficients, you use the result, which actually follows from this idea that the integral over any closed loop is equal to 0. You have an explicit formula that describes each coefficient of the Taylor expansion. And let me remind you, this is the Taylor expansion. This is the coefficient at z minus z0 to the power n. You can describe it as integral over the a closed loop containing the point z sub 0. And again, in constructive mathematics, if the function f of z is computable, then of course this integral is computable too. And so you have explicit algorithms for computing all the coefficients, and that's exactly what Bishop did. So, and a few some time ago, we actually it was motivated by the call for papers for this conference. We started looking at it with Olga, who is my wife and my co-author in many papers. And we took into account the following, that Bishop's derivation is based on the usual constructive mathematics, where every algorithm, no matter how long it takes, is considered to be an algorithm is considered to be efficient. So on course, the more realistic way, since we are talking about possible physical applications, is not so much to look at all possible algorithms, but to look for algorithms which are feasible. And at present, of course, the best known definition of what is feasible is polynomial time. There is a book by Kerry Core, and there was actually other papers on how constructive mathematics will work if we restrict ourselves to polynomial time algorithms. And what we are trying to show here is that in this case, Khalfin's dream can, or I would be more cautious, may be materialized. Let me explain what we have in mind here. So yes, there is an algorithm which shows that for every computable macroanalytical function, we can compute all the terms in its Taylor series expansion. This is the computations. But what we will be showing is that actually the computation of this algorithm turned out to be growing exponentially with n. And that means, based on the definition of feasible algorithm, that this algorithm maybe is not feasible. It's not a theorem, and I'll explain later on why it's not a theorem and why I don't know how to prove such a theorem, not how to formulate such a theorem. So here's an explanation. So we have a computable function. What does it mean, computable function? It means given z, we can compute f of z. And again, I'm just going to the basics of mathematics. And for simplicity, we can always assume that we know the upper bound on the derivative of this function. The function is smooth. That's whole idea of complex analysis, that we assume that the function is differentiable. So now we need to use this formula. So how the simplest possible case is, as a loop, to have simply a circle of some small radius around this point z sub 0. Why small radius? Well, first of all, if the function is not changing that much, that's easier to compute because you don't have to divide into many possible subintervals. Two, because you avoid possible poles and everything. So in this loop, the absolute value of this is a constant. So we want to compute a sub n with some accuracy. So that means we want to compute this integral with accuracy 2 pi times epsilon, because this here is divided by 2 pi. So a natural way to compute an integral is to compute the corresponding integral sum. So what is an integral sum? You take some points over there and you take the values on the nearby points differing by small distance h. And so in this approximation, we approximate each function on each small interval of length h, or between these 2 points, by the value at the midpoint. The accuracy of this approximation can be computed like that based on this basic theorem of calculus. It's smaller than the derivative times this value times the difference between the values z. The values z differ by no more than h over 2. This maximum is here. And so you can do some crude approximation of the value of this function. G of z is approximately equal to f divided by this r. And so the maximum is approximately equal, bounded by this bound on the derivative, divided by r to the power n plus 1. So this approximation accuracy has this form. So to get we want accuracy epsilon prime, which is epsilon divided by 2 pi. So we want this term to be smaller or equal than epsilon prime. In the kind of most relaxed case, it should be equal. So we have the formula for h for the distance between 2 points. It's proportional to r to the power n plus 1. And so how many points do we need on the circle of radius 2 pi times r? Number of points can be obtained by dividing the length of this circle by the distance between the 2 points. In other words, we have r to the power minus n points. And this is exactly exponentially growing with n. That's exactly what we are trying to show. So this grows exponentially with n. Now, why is this kind of waving hands and not a mathematical theorem? Well, the real application that we have in mind is quantum field theory. That's what Professor Khalfin was interested in, and that's where the problems are. And the big problem, as many of you probably know, is that the quantum field theory, there is no consistent mathematical formulation. So it's not like we cannot prove the theorem, it's just we cannot even formulate it. What do I mean by no consistent mathematical formulation? If you look at the existing equations, it is well known and is written in the textbook. So yes, you can expand in Taylor series and start computing the terms. At some point, the next terms in this expansion decrease, 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 and you seem to be converging, but then they start diverging. Moreover, there are very simple examples, including examples from electrodynamics, where you actually get infinite results. And there are some tricks that people use to make them finite. For example, instead of assuming that electron has a finite rest mass, they assume that this mass is kind of potentially infinite, and then it cancels out with the energy and so on. So there are lots of tricks, but there's no precise mathematical formulation that we can use to prove. And that's one of the reasons why, for example, about quantum computing, you may have read that nobody has proved whether quantum computing leads to, especially with quantum field theory, whether it can solve kind of equivalent, whether you can get more from quantum computing than from actual computing. It's not only because people cannot prove it, it's because they cannot even formulate this problem in precise mathematical way. So why this result may be interesting? So first of all, it may be interesting to theoreticians because then that's same idea. Unfortunately, Professor Khalfin is longer with us, but physicists are still interested in this problem. So it would be nice to be able to provide physical theories with physically meaningful mathematical foundations. So it's kind of a different mentality, which I learned when I started working with physicists. In mathematics, if you have some very complicated proof, you are kind of applauded. That's great. People think you are very smart. In physics, if for some physical phenomena you have a proof which is very complicated, people start thinking, well, something is wrong here. There has to be a simple, more physical proof. You cannot be that complicated. Another thing is that's what is even more practically important as opposed to kind of philosophically important is that what happens in practice is that every time we encounter a physical process whose properties are difficult to compute, it may be possible to use this process to speed up computation. This is a very old idea. Nowadays, everybody knows this idea from quantum computing, and that's idea starting with Feynman, although he didn't have formulas, but he had the general idea. Feynman, the famous Nobel Prize winner who wrote his textbook on physics, he realized that since many things in quantum physics are difficult to predict, more difficult than in classical physics, so maybe using quantum effects in computing can speed up computations. And indeed, turns out that what we call quantum computing is a good example of how this speed up can be achieved. But the whole idea actually can be traced to Lobachevsky, the founder of non-Euclidean geometry, living in the 19th century, who, when he proposed his non-Euclidean geometry, he actually explicitly said that many things in non-Euclidean geometry are more difficult to compute. One thing he had in mind was, for example, that the volume of the sphere, the volume of the ball, is not r cube, it's actually some combination of exponential functions. So he thought this may be a good, fast way to compute these exponential functions. So maybe by using this, we can actually extract something. And there are many schemes pretending or possibly causing to extract some computations from quantum field theory. Who knows, maybe something like that with analyticity can also lead to some physical phenomena. So maybe if we measure the corresponding Taylor coefficients, that can lead to another efficient quantum computing scheme. And these are the basic references. This is a Bishop's book that, of course, was overcome later on. But I think from the viewpoint of mathematicians, the first Bishop's book is still, to my big surprise, is still cited because this was, I think, the first book written by actually mathematician who switched to constructive mathematics, who showed that many things in constructive mathematics can be described in ways understandable to mathematics. This is a modern version of Bogolyubov's book that describes how this analyticity, macroanalyticity is used in quantum physics. Well, reasonably modern, it's 1990. This is the Professor Lifshitz paper, which, among other things, proved that the results that later Orevkov, for which Orevkov later provided more constructive proofs. This is Orevkov's paper, and I think it has an English version. I just didn't find it. And this was something that was obtained, actually was supported by some grants. So thank you very much. And I will be glad to answer all the questions. And I apologize if I went too fast and assumed too much about physics, but I'll be glad to explain because we still have time. Thank you very much.
Thank you, Vladik. Any questions or comments?
I want to say thank you for a very nice talk. And I wanted to ask something about the integrals that you talked about, taking exponentially many points, if you can hear me.
Yeah.
Yes. So you mentioned it takes exponentially many points to evaluate the integral. And so I guess that probably this procedure could be carried out in polynomial space. And so, of course, then you immediately hit the open question of whether polynomial time is equal to polynomial space.
Right. No,
so
of course.
It's not just the question of whether quantum field theory is well formulated, I guess, but also there's basic questions in complexity theory that get exposed by this.
Yeah, but at least, for example, in normal, that's what kind of, actually, I gave a talk myself some time ago in just the beginning, but then Kerry Core kind of monograph takes care of that. In general, it is known that the problem of computing the integral of computable function is actually NP hard in some reasonable sense. So you can basically reduce it to satisfiability or something. So here the question is, what happens if we limit ourselves to complex valued functions related to quantum field theory? So will this NP hardness preserve? But yes, you are right, absolutely right, because who knows, maybe P is equal to NP, and this what is NP hard can still be done in polynomial time. And yes, absolutely, it can be done in polynomial space. You're absolutely right.
And if I could follow up question, if I understood your proof correctly, you were using just the first derivative of f to bound the number of points. And
yes, because it's in complex values, it's sufficient, because in complex analysis, once the function is analytical, once the function is one-time differentiable, it is analytical. Right. So you don't need any more. Yeah, but if you add, actually, if you add second derivatives, you still don't get, you still get the exponential bounds this way. It won't help.
Okay. Yeah, that was going to be my question exactly. What if you added more derivatives, but it doesn't
right.
help? Okay.
Yeah, if you add finitely many derivatives, you get slightly better estimates, but again, these are estimates. This is not proofs. You get slightly better estimates, but still the number of steps, the computational time you need to compute this integral is still exponentially growing with n.
Thank you.
Other questions, please? Vladik, I wanted you, to ask you to clarify something. You mentioned functions computable in polynomial time in connection with functions that operate on complex numbers and return complex numbers, right? So I'm wondering, do I understand it correctly that this is a function that, say, takes a Turing machine that calculates approximations to Z and returns a Turing machine that calculates approximations to f of Z. And this function from Turing machines to Turing machines is something that you want to be efficiently calculable in polynomial time. Is this the kind of computability you talk about?
I didn't want to go into this philosophical details, but I would aim more for заполнение, for the fillings, rather than Z as Turing computable. So what I have in mind is more in line with what is called computable analysis. So what you have is a black box that, given n, produces a 2 to the power minus n approximation to Z. And that's kind of the basics of carry core results and everything. And then what you do, it doesn't have to be, actually, it cannot be that this Z is computed by a Turing machine, because in physics, you have to consider, well, you have to consider also random sequences which clearly are not computable by a Turing machine. So Z is kind of given by a black box, well, in line of whatever Chernoff scheme or Levin's axioms. And what you can do is you can do the computations, and at any given moment of time, you can ask that black box, what is the corresponding approximation to Z? And you can use that approximation in your computations.
Thank you. Any other questions?
When we had a,
yes,
sorry.
I wanted to thank you, but if you have anything else to say, please do.
Right. No, in our seminar in St. Petersburg, Professor Shanin always said, if there are no questions, that means one of the two things: either everybody understood everything, which is a rare case, or nobody understood anything, in which case it's a big disaster. So I did have some questions, but I hope it wasn't completely not understandable.
You had two questions. I think that's the ideal number of questions.
Okay, thank you.
So thank you, Vladik. And let's take a break and reconvene in